Okay, now this topic, that is another one, that is we call this is the radial-basis-function neural network. That is another kind of neural network topology. Yeah. Okay. Take a look at this slide. This diagram, it just shows you the radial-basis-function neural network. It looks very similar to the multiple layer feedforward neural network. Yeah, but the difference, that is, we can find out that the only difference, that is in the hidden layer, that is, instead of using some other activation function we use in the feedforward neural network, we mainly use the radial-basis-function. Yeah, so I'm going to let you know what kind of function it is. In the first layer, that is the activation function, that would be a linear function as we used before. And then the output layer, we can use any activation function we have learned before. So we have three layers: input layer, hidden layer, output layer. In the input layer, we have d input x1 to xd, that is a d-dimensional space input. And then so note that in the hidden layer, we do not have the bias, and we do not need to have the bias. And then so from the hidden layer to output layer, in the output layer, we have the bias right here. So this layer right here, it is exactly the same as the multi-layer feedforward neural network. I mean in the output layer. Okay, now take a look at this one. Another difference that would be if we are going to zoom into one of the hidden node. For example, when we follow the red line right here, and then x1 going through the red line, and then x2 going through this red line. So we are going to look at this hidden node and then draw it right here. Zoom into this hidden node. We have two elements. The first element, that is this L2 norm. We are going to calculate the distance. And then the output of this L2 norm, that is dj, we define it right here. So that means in this input layer and hidden layer, I do not put any connection weight right here. Actually, we have a C, that is the connection weight, that is the center. But the use of the center, that is different from the use of W in the multiple layer feedforward neural network. So this is the definition, or how do we calculate this dj? That is given right here. That is the L2 norm of x. X, that is the x input. We have x1 up to xd in d-dimensional space. The x right here. And then c, that is the value of cj1, cj2 up to cjd. So the notation is similar to what we have before. J, it means that is the, we are talking about the jth hidden node. Yeah, the jth hidden node. The second subscript, that is corresponding to the input x1. When it is 2, it is the x2, I mean the input x2. So when you look at this diagram, it will give you a little bit better idea. That is corresponding to hidden node J. The C value, that is in this connection link, that is the first subscript, that is J. If it connects to the first input x1 and then the second subscript, that is 1, and so on. So this dj, the L2 norm, if we are going to expand it using this x as well as this cj, and then so we will have the square root of x1 minus cj1 square plus x2 minus cj2 square up to the last element, xd minus cjd square. Yeah, so this is the definition of this L2 norm. So once we calculate this dj and then feed it into this radial-basis-function h, we can just find out yj. So we can represent yj as h of dj or h of L2 norm of x minus cj. Yeah, they refer to the same thing. So this table just summarize what kind of formula for Gaussian function or radial basis function we can use, and then which has different kind of formula. The most common one, that is the Gaussian function, that is exponential term of this dj divided by 2 sigma squared. So for this one, dj, that is calculated according to the x input as well as the center. Yeah. So this sigma, that is the width of this Gaussian function. Yeah. So we have to define this by ourselves, yeah, by trying error whatever way, and then later on we have some way to determine this value of sigma. In some other function, you will just find out that we can have more than one parameters. We have sigma and beta for this kind of function. Yeah. Okay. So when we talk about the input-output mapping, it means that we would like to find out the input-output equations of this radial basis function. When we fit in x into the input layer, and then what value of z we are going to obtain. Yeah. So if we are going to zoom into one of this particular node, following the orange line, and then we draw it right here. So y1, y2, yj, ynh. So we have this input right here. When we talk about the hidden node j, that is this one, and then when we zoom into that, this one, that is the new one, what we have with it before. Yeah. So let k, that would be the weighted sum of y1, the linear combination of y and wk. Yeah. So y1 times wk1 plus y2 times wk2, so and so. So we obtain this net. And then let k, that would be the input of this function. So z would be function of let k, and then net k, that would be this weighted sum function or linear combination function. So we compute, when we know what value of yj it is, we can compute zk, that is one of the particular output. So we extend this idea to all this output when we change the value of zk in this equation. Yeah. Okay. And now y given right here, as we have seen in the previous slide, y can be written as this function. So we are going to substitute this function into this expression into the yk. We obtain this equation, this expression. Relate x to z. Yeah. So that means when we plug in the sample x into this function, we are able to compute all the value of z right here. Okay, the concept, the idea is more or less the same as we have done in the feedforward neural network, so I'm not going to go through or to repeat the details again. Now, the training goal, that is similar. Yeah, so for this cost function or the training error, we use the same concept. We have the stochastic backpropagation before, and then that means we can compute the training error with respect to one of the training sample, and then for this j right here, that is the sum of all the training error corresponding to the p samples. That means that is given right here. J, that is the training error corresponding to the first sample denoted by J1, and then the second sample, J2, and so on. So this equation, that is exactly the same as this one. So we refer to this slide to recall the memory. Yeah. Okay. Now, when we have this radial basis function neural network or the RBF neural network, now what we are going to do, that is, we would like to determine the center, the C value in this layer, as well as the connection weight in this layer. So we are going to apply two kind of learning paradigm or two learning algorithm to determine the value of C and W. Usually, to determine C, we are going to use the unsupervised learning. Yeah. So we have two approaches to do that. The first one, that is, we are going to fix the center. So randomly choose the value of these centers after you know the number of hidden nodes. And then so another one that would be the clustering based approach. That means we are going to apply the clustering method to the training sample, to the center of the clusters. They are the centers in this layer. I'm going to give you the details later on for these two approaches. And now, when we move on to the WKJ, that is this value in this layer, that is, we could use the least square method to do it. That means if this function is a linear function, for example, actually, if it is a linear function, it will make your life easier. If it is a nonlinear function, we can still use the least square method to do it. Yeah. So another one, that is to determine WKJ using the backpropagation approach as well. Yeah, so we have done that before. Now, so there's a remark right here, that is, for some scenario, we can also use the least square method to determine CJ as well. Yeah. Okay. Now we are going to talk about the fixed center approach. That is this one. We are going to talk about the unsupervised learning and then the fixed centers approach to determine the connection weight, the center in this layer. And now, this method that is very simple and very quick because we do not involve any learning because everything that is by random. But the thing is that we have to choose the number of hidden nodes right here. This number of hidden nodes that is less than n, and that is the number of samples in the training data set. For example, this diagram just show you the training data set. For example, we have the x, the input in d-dimensional space. That means we have d input for this neural network, and then so we have n sample. Yeah. So this column, that is sample 1, this column sample 2, this column sample n, and then associated with each sample. And then so we have the target value. This is the target value for pattern 1. That means when we input this x value into this RBF function, we expect that the output z would be this value. Yeah. But at this stage, we do not need to use the target value because we do not use the supervised learning. Yeah. We use, that is this approach, that is we are going to randomly choose some centers. Yeah. And now this is the procedure. Because nh, that is less than n, the reason why that is explained right here, because in this procedure, so for example, we have n that is 100, and then nh, for example, we are going to choose 5, and then 5 less than 100, and then now we have 5 hidden nodes for this RBF function, and then among this 100 samples, we randomly choose 5 out of this 100 to be CJ. For example, I choose this one to be Z1, this one to be C2, and then so this one to be C3, something in between, and so on. We choose 5. And because we use the Gaussian function, we have to determine sigma. Yeah. Now the sigma, that is governed by this expression, and the sigma, that is something inside this Gaussian function in the hidden layer. To determine sigma, why we have the sigma j right here and we don't have sigma j right here? The sigma j, it means that it is corresponding to each hidden function, the Gaussian function in each hidden node. It means that this j, this is sigma 1, this is sigma 2, sigma 3, and so on. It just tells you that we can use different value of sigma for each function in the hidden layer, but of course we can use the same sigma for across all these functions. Yeah. So we have two options to choose this sigma. The first one, that is we are going to find out the row max divided by the square root of 2 times the number of hidden nodes defined in step 2, and then another approach to choose sigma, that is 2 times the row average. rho max, that is the maximum distance between the chosen center. That is the chosen centers right here. In the next page, I'm going to show you the example. How do we determine the rho max and then what it means by the maximum distance between chosen center, or the rho average, that is the average distance between the chosen center C right here. Again, I will demonstrate that in the next slide. And if we have some other parameters in this layer, we are going to randomly pick those values. Yeah. Okay. This is the example. Assume that we have 10 input samples in the training data set. That means we have x1, x2 up to x10 in this training data set. And now denote that by x1, x2 up to x10 as I mentioned right here. Now, if we are going to choose the number of hidden nodes to be 3, that means in the number of purple nodes right here, that is 3. Now, I'm going to randomly pick C1 to be x5, that is one of the sample in the training data set, and C2, that is x2 right here, and C3, that is x9. So different people may choose different hidden nodes, may choose different samples as C1, C2, C3. Yeah. Anyway, according to what we have chosen, now I'm going to determine what sigma value it is. So the first option, that is using the rho max, because we have 3 centers, so we can calculate the distance between centers. 3 centers, we have 3 combinations. C1 minus C2, that is the distance between center 1 and center 2. C1, C3, that is another combination, and C2, C3, that would be another combination. If we have more centers, and then so we will have more combinations right here. So according to this example, within these 3 options, we are going to pick the one with the maximum distance. Yeah. So if this one that is 10, this one that is 2, this one that is 25, we are going to pick rho max as 25. So once you know that rho max, and then you know NH, that is 3, sigma j, that is calculated. So we are going to apply sigma j, that is rho max divided by the square root of 2NH to the Gaussian function for all this hidden node. And then the next option, that would be the rho average. The same ideas, that is, we consider all the combinations of the C difference, and then C1, C2, C1 minus C3, C2 minus C2 minus C3. Sum up all of them divided by 3, because we have 1, 2, 3 terms. This is the average distance between center. Yeah. So this is the second option for you to find out the sigma value. And then if you choose this options, you choose this sigma for all the Gaussian function in this hidden node. Yeah. Okay. Now I just explained the first unsupervised method to choose the value of C, yeah, using the fixed value, and then the next method, that is using the clustering based approach, that is I'm talking about this approach. We're still talking about the connection weight, the centers right here, yeah, but using different methods. Again, we have the training sample, the training data set, and then it could be any number, any dimensions, but this figure just shows you that we only have x1, x2. So that means this one we only have 2 input. Yeah. Otherwise, we are not able to plot it in this figure. So each point right here, for example, this point that is corresponding to x1, and then this point is corresponding to x2. So this is the column. Yeah. So we have many points right here. And now we can apply the k-means clustering. I'm going to introduce that in the next topic. Yeah. Okay. So the idea, that is, we are first, we have to determine the number of clusters. So this example just shows you that we have 3 clusters. You can extend this idea. You can extend that to 4 cluster, 5 cluster, whatever number you want to use. But anyway, in this example, we use 3 clusters. So when we apply the k-means clustering, it will automatically tell you which sample belongs to which cluster. For example, the wet samples, that is the cluster 1, based on all these sample points, the average, that would be this center. So we call this is C1. So according to the calculation, according to this formula to calculate the center, so this means that for all samples belongs to this cluster, and then sum up all of these samples, that is to sum up all these wet points, and then divide by the number of them. Yeah, so it will give you this center. The same applies to the blue sample. Sum up of all these blue samples and then take the average. It will give you this is C2, and then when we consider all the green points, this is C3 and so on. So now C1, C2, C3, that is the C1, that would be the center for the first hidden node, and then the second hidden node, that is C2 and so on. It just gives you the value of C right here. Okay, now we have 2 methods to determine C. The first one, that is to use the fixed center approach. Randomly pick some centers from the samples in the training dataset. The next method, that is we apply the k-means clustering to the training dataset, and then so which will give you C1, C2, C3. Yeah. Now we are going to talk about the determination of the output weight. That is, how do we determine WKJ? Yeah. So once we define C, we can determine WKJ. Now we are going to use the least squared approach. Assume that the function, that is a linear function. So this is a linear function. That is the f, that is a linear function. Yeah, as I mentioned before, if it is a nonlinear function, we can still use the least square approach, but we have to look at that case by case, because some of the nonlinear function, it is not one-to-one mapping. Yeah, linear function, that is one-to-one mapping, so we can just make our life easier. So just to recall that zk, we can have this equation. That means once you find out what value of y, and then so zk, that would be y1 times the connection weight here plus y2 times the connection weight here, and then so this is the weighted sum equation. So once you have this equation, the only unknown, that is WKJ, because we have the training data set. The training data set say when we fit in x1 into this equation, we are able to find out the zk. Yeah. So zk, that is this value. If we are going to talk about z1, and then we will have the same equation but different value of WK. Yeah, but at the moment we do not know what value of WKJ it is. Yeah, so we are going to formulate the problem like this. So when we have x1, plug it into this equation, and then this equation can be expanded into the first row. y1 times WK1 plus y2 times WK2 and so on, that is this one. According to this x1 and the target data set, we know that we expect that when we input x into this RBF neural network, and then the target output will be this one, T11, T21, TC1. Say this is 1, this is 0.1, this is 2.2, and so on. We have some numerical values right here according to the training data set. Yeah. So When we feed in x1, the first input, into this function, we expect that we have a fixed value right here. For example, this k, that is talking about the kth output. Say if the kth output k, that is 2, that will be t21. So we will have a value that is, for example, this one, that is 0.1. K, that is the kth output, the target value for the kth output. The second subscript right here, that is corresponding to the first samples. If we fit in x1, that one, it means that that is the first sample. If we are going to fit in x2 into this equation, we have the same unknown right here, wk. And then this is the second sample, and then so we will have the next target value. That means when we fit in this x value into this new network, we expect that this z will be this t22. Yeah, for example, t22 would be 1.2, and then this 2 means that that is the target value at the k position of the output corresponding to the second samples in the training data set. So if we have p samples, and then so we can just do it row by row, and then so we just construct the target output right here. That means these values, because when we load c, when we fit in x, we can compute y, we can compute the y value. So all these values, they are known. So we have the numerical value right here. The only unknown, that is w. The same for this one, tk, according to the training data set, we have the numerical value right here. So in matrix form, we denote this matrix. It can be a square or a non-square matrix, and then phi of x. Yeah. So this is a constant matrix. And then the only unknown, that is wk, we have these unknown. Tk, that is a lone matrix, that is a numerical value. So we have phi times wk equals tk, and then this is the compact form. If it is a square matrix, as I mentioned before, the only unknown, that is wk. So inverse phi times tk, it will give you wk. So that means, of course, it depends on whether this phi is invertible or not. We assume that it is invertible. Yeah. If it is non-invertible, that means the training data set is not well defined. Yeah. The next scenario, that is non-square matrix. If it is non-square matrix, we can still use the pseudo inverse, and then wk can be calculated by this equation. Okay. Now, I already mentioned about how to determine wkj using the least square method, assuming this function, that is a linear function, and then another method, that is we are going to use the backpropagation. Yeah, the backpropagation, that is we are going to find out parcel j, parcel wk, and then so we are going to update wk using this update rule we have seen before in the feedforward neural network. This idea, that is exactly the same as what we have done, and then we can extend this idea to the sigma value as well as the c value right here. So that means if you would like to update sigma value, if you are able to find the change of j with respect to this sigma, and then you can also update the sigma using the backpropagation algorithm. The same applies to c. So it depends on whether you are able to find this parcel j, parcel cj, as well as parcel j, parcel sigma j. Yeah. So if the function is differentiable, and then most likely you are able to find out these two guys. So we can still use the stochastic or the batch update algorithm, as we mentioned before, to do this update. Okay, and now we are going to take a look about the similarity and the differences between RBF and the multiple layer perceptron neural networks. And then the similarity, that is, both of them, they are universal approximator. Yeah, so that means we are able to use either of these two neural networks to approximate any nonlinear function, continuous nonlinear function in a compact domain to any arbitrary position. So both of them, they are feedforward neural network, because when we present the input and then we can collect the output right here in between without loops. So this is a feedforward neural network. The difference is RBF, we only have one hidden layer, but for the multiple, this is the MLP neural network, and then this is the RBF neural network. So you can just find out that for the multiple layer neural network, we can have more than one hidden layer, but for RBF, usually we only consider one hidden layer. Yeah, okay. And for RBF network, we are going to use the Gaussian basis function, and then so while when we consider the MLPNN, we have different set of activation function used in the hidden layer as well as the output layer. And another thing, that is RBF, we are going to compute the DJ in the hidden layer. That is the distance between the input and the center. Yeah, we use the L2 norm to find out DJ. But for MLP, that is, we use the inner product. That means right here we are going to do x1 wj1 plus x2 wj2. That is the let value in the hidden node. Yeah, so this is the inner product. This is the distance. So for RBF, the training, we could use the mixed mode, the unsupervised learning to determine C, and then the supervised learning to determine W. For MLP network, both W in these two layers, we use the backpropagation to update the W. Okay, so finally, the conclusion. Yeah, the conclusion, that is just to emphasize some key concept as well as the important things about the neural network. 3 layers neural network is a universal approximator. Yeah, so that means we cannot use 2 layers neural network and use it as a universal approximator. So at least we have to use 3 layers, and then but how good it performs or whether it can approximate anything depends on the initial condition during the training. That means when we apply the backpropagation algorithm, the connection weight is randomly chosen, and then if it is randomly chosen gradient descent approach, that is, sometimes it will be trapped in the local optimal. So that means if you are going to start with different initial condition, the update of W will be different. That means different initial condition will give you different settings, different values of W. Yeah, and then also if you are going to choose the different number of layers, different number of hidden nodes, as well as different kind of nonlinear activation function, and then so it will give you different performance. When you apply the backpropagation algorithm, we require that the activation function to be continuous such that it is differentiable. Yeah. So as I mentioned, the number of hidden layers, we have to choose it maybe by try and error. So we start from, for example, 5, 10, 15, and so on, to choose which number of hidden layers as well as hidden nodes will give you the best performance to avoid overfitting or underfitting. Yeah. And also during the training, we need to have at least the training data set in order to apply to train in order to apply the backpropagation algorithm to train the connection weight. And then if we are going to use the validation set, it will give you some idea when to stop. If you are going to have the test data set, that is to give the trained neural network some unseen example, which actually we are going to apply this trained neural network to the real scenario, yeah, or the real situation. Instead of using the feedforward neural network, another option, that is the RBF neural network radial-basis-function, and then the training of the radial-basis-function, we can use the hybrid mode, that is combining with the unsupervised as well as the supervised learning. Yeah. So this is the end of this topic.